Are you ready to start? What are you just sitting there? Look at me. We can look at the camera and say, hey, but not yet. All right, ready? Hey, everybody. Today we're going to talk about why the colors that we see or why objects we see are the colors that they are. Where color comes from and why we perceive them the way we do. Looking into how the human eye works and the colors there. I do have my boys. Can you introduce yourself?
My name is JW and my name's Robin.
Right. And they're going to help me by just kind of going through. So, boys, I just have some questions for you. What color is the sky?
Blue.
Well, that's not the sky. Oh, okay. It's blue. Sky is blue. So when you look at the sky, it's blue. What color is the sun?
Yellow.
Okay, so the sun's yellow. Now, let's name some of these colors here. First color here. What color is that?
Red.
All right. JW, what color is that one?
Black.
Robert, what color is that one?
Blue.
JW, what color is that one?
Ooh, turquoise.
Turquoise. Nice. Robert, what color is that one?
Orange.
JW, what color is that?
White.
And Robert, what color is that?
Pink.
Pink?
Purple.
That's purple?
No, pink.
Pink. Okay. Good job, boys. All right. So now we're going to shift and say, why did they name the colors that they did? How did their brains know to answer that? You guys want to say bye?
Bye.
All right. So we'll start out with kind of how you see light, how you see things. Starts out, you have your eye. Right? Your eye needs to get light into it. Or if there's no light, then everything just looks dark, looks black. But if there is light, whether you look right at that source of light, like a light bulb, or you look at the sun or something, or you just look at an object that has the light reflecting off of it, and then you see the object. The light has traveled either from the source or from the object right through your pupil, so through the front of the eye, and then it projects through a lens, projects on the back of your eye, which detects all the different parts of the light, and you can see the color, or you can see the different shapes and things. So there are two cells back there on the back of the eye. You have rods and you have cones. Rods say yes light, no light. They allow us to detect, oh, there's something there, or there's not. You can see bright lights, things like that. Whereas the cone cells actually detect different frequencies of electromagnetic waves. And so, move out of the way here. There are, let's see, L, M, and S. You can't see the S there. I'm blocking that. But there are L, M, and S cones. Now, no one recalls them L, M, and S cones. Everybody just they're just different cells. Everybody calls them red, green, and blue cones because of the primary colors of light that they detect. And more on that in just a second. So, your eye, light enters and gets detected by different cells, particularly red, green, and blue cone cells that say yes red, no red, yes a little bit of red, a little bit of green, a little bit of blue, and they get activated different amounts. Okay, so here we have kind of a projection of what each of the different cone cells. So we've got blue cone cells detecting some light, and so if a frequency of light that's in here in the purple or blue range or the cyan range comes in and hits your eye, it actually activates the blue cones. Whereas something comes in the green area is going to activate the green cone, and if light comes in the reddish area, it's going to activate the red cone, basically. So this is the actual setup of your eyes. I'm going to go to a slightly different setup where I can kind of change these to show like, oh, if you didn't have green cones, then you would see only blue and red and a mixture between. Then you'd have some missing things, but we can't, so we can see other colors because we have that third cone. Dogs, I believe, only have blue and green cones. So dogs, everybody says dogs see in black and white. Really, they see in like a blue-green kind of mixture. So they don't see red and that. Anyway, I'm going to swap over to something else that's a little bit different. So this will be the setup we use when I kind of describe what's happening and what your eye is seeing. Now, first off, what are the colors of the rainbow? Or I should say colors of the spectrum. Well, you've got red, orange, yellow, green, blue, indigo, and violet. officially. Those are ridiculous colors. I don't know why they have that colors. There are better colors that we could say. So, Mr. Ager colors. Ready? 700 nanometers, red. 650, so we're going to count down. We're going to get smaller and smaller wavelength, higher and higher frequency. So 700 is red. 650 is orange. All right? 600, and I really should have it a little bit down. 600 we're going to call yellow. Now it's a little more green yellow, but we're going to call 600 yellow. Orange, then yellow. All right? Then 550 is our green. 500 is what we call turquoise, what JW called turquoise, but really the official color is cyan. And then 450 is blue. And then 400 is violet. So once again, red, orange, yellow, green, cyan, blue, and violet. And now we're evenly spaced, and we've named each of the colors at even intervals through the spectrum. So those are the colors that I want to use today. One more time, Mr. Ager spectrum colors: red, orange, yellow, green, cyan, blue, and violet. All right. All right. So what color of light do you see when you look at different colors? So it's got a setup here. Got a guy. I'm not going to use a guy. I'm just going to use a person with a brain. And I'm going to shine different colors of light at their eyeballs. And you can see above their head what color they see. All right, so we'll start out. I've got white light selected. Turn on the flashlight. You can see my white light shoot into the eye, hits it, and the person thinks white. Well, white's not a color. It's not in the color here. So rather than thinking of this as, beams of light, I want to think of light as particles or photons at different wavelengths. And white light is all of the photons together. So instead of that, we're going to use it as photons. So white light is all the photons coming out, red all the way through violet. And lots of little dots are now shooting out of the flashlight, hitting the eyeball. But because you're getting all the different rods activated, and we're activating the red, the green, and the blue cones, since I'm activating all three types of cones with this beam of light, my brain is interpreting those three signals from the cells as white light. All right, if I change though, and now I start to send in different colors, let's say I send in red light. Let's go hit red there. I send in red beam or particles of light and hit the eye. Well, now I'm at the 600 or 700 nanometer length, which means it's activating the red cones, not activating the green or the blue cones. It's only activating those red cone cells. And so my brain is only getting a signal from those red cone cells. So I'm saying, hey, that's red. That's red. So the certain frequency, 700 nanometer, kind of red colored light activates the red cones. Right? Likewise, if I jump over to green light, now I'm activating, I'm at about 550. I'm activating the green cones and not the red or the blue. So because it's only getting a signal from the green cones, my brain says, hey, green. And finally, blue. If I hit blue, then I fully activate the blue cones and none of the others. And so my brain says, hey, that's blue light, because I feel that 450 nanometer light hitting my eye. So different colors of light are activating that. Now, what happens when something like yellow light or orange light, yellow, hits my eye? Well, yellow light, there's no yellow cone. So how does my brain interpret that yellow light as, well, yellow? What happens, if we look back at the three different humps, yellow is in between my red and green on the spectrum. So when that frequency of light enters my eye, it actually activates both my red and my green cone. So when my brain gets a signal from both the green and the red, it doesn't say green, red. It sees a whole nother color. And in fact, it says, hey, that's yellow. So a yellow object is actually, by my eye stand, activated green and red cones. Yeah, the light is yellow light, but it's actually activating two cones, and then my brain is doing the interpretation into the color that it sees. And this is going to get really cool on Thursday. So let's jump over to the next one that's kind of in between green and blue, which we call cyan. JW called turquoise. Cyan light, right? So I'm in between the green and the blue. Cyan light is an activation of both my green and my blue cones. And then finally, violet. What is violet? When I get down to violet, notice on the spectrum, violet's at 400. And we look at the hump, and it's at the end of the blue hump. So it's not at the peak of the blue hump. So violet, our brain actually interprets violet by a low activation of just the blue cone. So if the other side of that, if we activate a little bit of the blue cone, but you're also getting green, well, then it's going to say that's cyan. But if it's only getting blue, but a little bit of blue, it's actually going to view it, it's going to interpret that as purple or violet. We'll call it violet. Violet's a very specific color because ultraviolet is the next one up. So that is why our eyes see color the way it is. Again, 3 different cones, red, green, and blue, and then you activate each one different amounts to produce all of the colors in the spectrum. All right, so hopefully that made sense about why light appears the color that it does when you look at the source of the light. But now I want to transition and apply that to the next step of why objects appear the way they do. First off, this is my daughter, Leela, who wants a marker. Okay, she's going to just hang out with us. I'm not sure she's going to contribute very much, but she's going to hang out with us during this one. So, color of objects. So why do objects appear the way they do? This is very simple. It's almost the exact same thing, but I just want you to visualize and think about it. First off, we start out with a source of light. You can't see an object unless light is bouncing off of it. So we're going to start with white light. Now, I've drawn the white light with red, orange, green, blue, and violet there. I didn't have a yellow, but all the colors of the rainbow. Because the sun, white, not yellow like JW said, it appears a little yellow, and we'll get to that tomorrow on Wednesday. But all the colors of the spectrum come out of the sun. Now, they don't come out like a rainbow, but I've drawn them like that. They come out all on top of each other. There's a bunch of particles, as we saw, a bunch of particles, and then they hit an object. And then so either one of two things happens. Really 3. It could go through the object. That would be clear. We're not going to worry about that. It's either going to be absorbed, so it's going to absorb that color, or it's going to reflect that color away. Now, if an object reflects all the colors of the light, they hit and they all bounce off, all colors, well then our eye will see all the colors at once, or it will see white. All right? But if instead, let's say that this car reflects only one color. What if it only reflects, well, if it only reflects red light, then we see the car as a red car. Well, what happened to the other colors? Well, the other colors were absorbed. So what colors were absorbed? Well, orange, green, blue, violet. All the other colors were absorbed. So for any object out there that appears a certain color, we know that it reflects that one color and absorbs the other colors. Hence my initial statement of from yesterday of what color do plants like? And the answer is not green. If it appears green, then it must be absorbing all the other colors and giving off, reflecting away that green light. So, color of objects, we'll go a little bit more with a simulation, and then you guys work on the worksheet. Thanks, and have a good one. All right, so now what color do objects appear? So, start out with, I've got a light bulb here that I can make a bunch of different colors, red bulb, yellow, green, cyan, blue, pink, and white light. But I want to do all of the things as white light. Now you'll notice white light, it's only showing red, green, and blue light coming out of that. More on that on Thursday. But for today, let's think of red, green, and blue as just the entire spectrum. So it covers red, green, blue, and also cyan, yellow, orange, violet, all the colors kind of in between. I know violet's not in between blue, but let's just call it blue since it's that final color. There. So if we think about all 3 colors as just all that, then a white light bulb, a white bulb producing white light will produce all of the different colors. Then I've got an object here, got my duck, and I can change the color of my duck. I can make it a black duck, red duck, yellow, green, cyan, blue, and just change the color of my duck. I'm going to leave it as a white duck right now. So a white light bulb, so all the colors hitting a white object. Well, this object is going to reflect all the colors. So the next step would be it reflects all those colors, and it reflects in all directions, but this is only showing you reflecting all the colors towards the eye. Now, we're not going to bother with filtering these colors at all, so I just want to go on to the next step, that all those colors hit your eye. Well, if all the colors at the same time hit your eye, what color does your brain think it sees? Well, let's see. Oh, it sees a white duck. All right, back it up a little bit, back to the white. What about if I had a red duck? If I had a red rubber ducky here. Again, white light, all the colors of the spectrum, blue all the way to red, are coming out. So blue all the way to red, coming out, hitting that red duck. But now the red duck is actually going to absorb everything but red. And the red light will travel off of the duck and hit your eyeball. And so your eye says, what color do I see? What color am I receiving from that duck? And sure enough, red duck. Now, key takeaway here, red light reflected, all the other colors, cyan, blue, cyan, green, yellow, orange, all those are absorbed. So this duck is absorbing those other colors, those other frequencies of light. It's only reflecting the red color of light. All right. Same thing if I look at a green duck, it's all the colors coming in, and then it's reflecting only the green. So now it's absorbing the red, orange, yellow, cyan, and blue, but reflecting the green. And if I look at a blue duck, the blue duck is reflecting the blue light and absorbing red, orange, yellow, green, cyan light. Now, what about a yellow duck? Or let's do a cyan duck. A cyan duck, and this is the way this little thing, interpreting it, is going to absorb that red, orange, yellow light, but it's going to be reflecting the cyan color and maybe some on either side of it. So it's showing you in this simulation that the green and the blue, so the cyan together, are coming and hitting your eye. So, but we're going to focus on just the idea that if you get red, then, or if it's a red object, then it's reflecting red and absorbing all the others. Now, what about a black object? What's it going to do? So let's back it up. Black object. So black object, light hits it. What reflects off? Nothing. Nothing reflects off. Black objects that are black, are actually absorbing all the colors that hit them. They don't reflect any color. And so when your eye sees other things around that object that are reflecting color, it's like, well, that thing that's not reflecting color, I'm going to call that black. And so sure enough, your brain thinks black. Yeah, so that's it. Use this, watch it again a couple times, a couple different parts, but should be able to answer all the questions. And if you're not sure exactly, guess on some of the more challenging ones at the end of each page are meant to make you think a little bit more. And then I'll do a video on the answers to those for tomorrow. Have a good one.